So we have test on Friday. I handed back your quizzes. The answer was 20 volts, and a lot of people made some silly mistakes. Some made more serious mistakes. I don't want to talk about it now. I want to get on the lecture. But we'll have, what we're going to do this week, we're going to have 2 lectures, today and Wednesday, on first order circuits, and then we're going to have a problem hour on Thursday before the test, so for anything that you can't figure out on the homework or anything like that, or the quiz, we can kind of bring it up then. If you want to stick around after class at times too, I can meet with you if you have some other questions to work out. Assignment 6 was due Friday, but can you get it to me end of day today, people who haven't turned it in yet? I know some people haven't turned it in yet. Is anyone still holding on to assignment 6? That was the op-amp one. Since that's going to be on the test, kind of need that. How many did you get? Did you upload it? Okay, cool. I didn't check the uploads yet, but I noticed it seemed like some people hadn't turned it in yet, so I was holding off on grading. But I'll get those back to you tomorrow then, so you have some chance to kind of look it over. Then I'll post a solution. So yeah. So any last assignment 6s would be appreciated today. And okay, so that is the original slide, and since I won't be able to write on it, I could probably open up a text box. Yeah, I could type in there. That might be better. I don't know. We'll see how that works. That's an option. The formatting is just, it drives you crazy on PowerPoint whenever you use PowerPoint. If you've never written a PowerPoint slide, it's like the 3rd level of hell. You spend all your time adjusting font sizes and stuff like that. It's ridiculous. Anyway, so the topic for today is first order circuits. We looked at inductors and capacitors last week, and I do want to tell you one thing about the grader for assignment 7. For those of you who haven't tried yet, it looks like it can't show you the grader because we don't have the freaking. I don't know why that's not working.
Well, my question was number 3 had like the units.
Yeah.
Included like sine of blah 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 with a t in it, but
right.
You integrate from 0 to 5. Why would you have?
You're not integrating from 0 to 5. You're integrating from 0 to t over the range of where t is going to cover anywhere between 0 and 5 milliseconds. Okay, so let me show you that on assignment 7.
Oh, 0 t. Yeah.
So basically, problem 1 is a function of time, right? You're going to take the derivative of the current, and it's a function of time. Yeah, problem number 2 is also a function of time where t is between 0 and 5. So your answer is going to be a function of time. It's going to be some kind of sine thing. Right? Well, the derivative of the sine is a cosine, right? So it's just going to be something times a cosine.
Cosine 200.
Whatever. And what the grader does, because the grader can only take a number, I can't have you input a formula, which is what the answer for these things are. So the grader has a blank, and then it says cosine of 200t 8 or something like that, right? And that's in the unit field. But that's actually just this is part of the solution. I just can't have you type that in because the grader can't parse all that stuff. The grader can only take a number. So what you got to do is you got to figure out what is the coefficient of cosine of 200t for the current, which is when you take the derivative of that, it turns out to be 0.2 or something. And the same thing for number 3. This is a function of time, and you only need to worry about this time interval, but you're not integrating from 0 to 5. You're integrating from 0 to t. Okay, and it shows you exactly. We did that in the lecture. If you're confused, bring up the lecture. It shows you how to do that in Wolfram Alpha. It'll do all that real easy for you in Wolfram Alpha. Practice. This is really what I was expecting you to use. Is just the computer tools to do this stuff, and then just plunk in the answer. And
let's say integrate blah from 0 to t.
Yeah. Okay. And the answer is going to be a function of time, which is valid over that time interval. It turns out this is actually going to make like a little pulse. It's a sinusoidal, something like a sinusoidal pulse. Oh, actually.
Those will actually have a 5 pi or ours says 5 to 0.
It's 5 pi.
Ours says 0 less than t less than 5.
Oh, really? It should say 5 pi. Fucking computers. Sorry. We should destroy them all before they destroy us. Yep, that's 5 pi.
That's one. Right, well, let me correct that. Yeah. That would have changed. Yeah, probably would have.
Okay, and then for this one, you're gonna take problem 2 and you're gonna find the power. Now that you've got the current and the voltage, you can find the power by multiplying them together. Yeah. Again, the answer for that is in the unit field, it's going to have the whole term which has t in it. It's going to be a function of t, and then you've got to figure out what is the coefficient in front of all that. Make sure you did the integration, did all the multiplication, all that stuff properly. Okay.
So Christian was helping me for part C when you find the max.
Yeah.
So then that's just going to be C equals pi n over 200 coulombs.
Pi n? What's
Because you're going to have all these.
No, this is only going from 0 to 5 milliseconds. Okay, so there's only going to be one max in that interval. Yeah, it looks like it's a squiggle, right? It just looks like I can't draw it, but it looks like it's a half of a sine wave.
Right.
Going from 0 to 1 to 0.
Okay. Well, because when
it looks like it should look something like that, okay, where that's 5, 5. And it's essentially a pulse. It's a sinusoidal pulse that we're doing it. It's an easy way to do a pulse across this thing, as opposed to doing some piecewise linear thing, which then you gotta integrate these different regions. It's a real pain in the butt. With a sinusoid, you can just integrate the one function. So again, the slides it tells you how to use Wolfram alpha. There's some hints here on how to do Wolfram alpha. These are just representative functions. This is not what you're going to integrate, but you got to figure out how to express what you want to integrate. And
the plan, that's just for the flying, right?
Yeah. If the initial value is 4, this is telling you how to do the integration. Hopefully not too confusing. Okay. Oh, I'm recording. Oh, but I'm not sharing the desktop. Sorry, Lisa, you didn't get to see any of that. Can you hear me now? What do you mean until I logged on?
Yeah, her microphone stopped working when she logged on. Did she?
Okay. All right. No, I don't know. None of my students want to talk on this. I think they're all shy. I know. Yeah, then you could interrupt my lecture and tell me, hey, I can't hear you.
Yeah, I'd be like,
Actually, the sound, I don't know how to get the sound on this thing, so I probably can't hear you anyway, even if you do have sound. So, anyway, continuing on. So we're looking at first order circuits. You got the handout, right? And we're going to look at a few different circuits. The source-free one means that source-free circuits means, oops, I got the wrong lecture slide over. Oh my God. I don't believe it. I fixed these slides last night. And I fixed them so well that I took out all of the comments on them somehow. Why did I do that? How did I do that? So now this is human error. The combination of human error and computer error is sometimes unsolvable.
That's how Chernobyl happened to him.
True. The irony is these things are actually really easy to solve. Sorry?
The problems are?
Yeah, they're actually really easy to solve. I mean, they're really not that complicated. You make certain assumptions to solve it, but gosh darn it, would be really nice if I had those marked up slides. I just did them last night over here, and I thought, well, and I was like, I usually make backups, and I was like, well, if I screw it up, they're on my other computer. And unfortunately, I should have just stayed home today. What am I going to do? Let's see. Is this really screwed up? Okay, no, this has it here. Okay, I do have it here. Good. Why did that? Oh, I know. So when you save it as a PDF, you have to click on options and say, yes, please include all the comments in ink markup.
So there's an option that you have to opt out of.
Yep. That's technology. I think someday we're going to have a completely different kind of computer, which...
No, but the interface engineering was that we were talking about at the time?
Yeah.
Do some more of that.
Right. Yeah, like, you mean Dan's talk?
Yeah.
All right. Well, actually, luckily I can actually recover from this one.
Are you minority report? Zoom? Yeah, put in hand. Put in hand. You'd be like, I don't go frozen. We're going to go around this death spot.
All right. Anyway, I think I should be able to just use this thing. Where is that? Yeah. Okay. So this first order circuit, what we call source-free, is also referred to as the natural response. And you might have, I don't know if you've run that. When you solve differential equations, have you used these terms before? There's like a forced response, and something where you're not forcing a response? No, you never heard of that before? Okay. That's called the natural response. And then there's a step response. You've heard of the step response, right? Differential equations, first order differential equations. Totally never heard of this before, right?
What you're using, I feel like I've heard the term.
Yeah. Okay, well, anyway, we're going to look at the natural response today, and then we'll look at the other one later, the step response. So yeah, so this is what it looks like. This is a typical first order circuit. What we looked at last week were just circuits with just resistors and just inductors and capacitors in them, but no resistors. And when you add a resistor, you actually now have what's called a first order circuit. If you have a capacitor and a resistor in the circuit, that gives you a first order differential equation when you try to solve it. So can you read the notes if I type them here? That's really small. Let me just, I can insert a text box. This will probably just, it always screws it up, but I'll try it. Just get it here. So what happens if we do KCL at node, well, at the top node? I was going to call that node A, but I can't mark that up. So what you would find is that IC, which is the current going to the left into the capacitor, plus IR, which is the current going to the right to the resistor, has to equal 0. Don't you agree? And IC equals the law of the capacitor? Nope. Nope. What's the formula for the law? Bring out your sheets, that cheat sheet I gave you, so that you don't have to remember all these things, although you should remember these things because they're kind of important. Yes, C dV dt, and then what's IR? If we have this voltage V at this node, call this voltage V, it's just D over R equals 0, okay? And so the first, this is the law of the capacitor. The second one is just Ohm's law for the current going to the right, okay? And there are various steps in solving this, which you probably don't want to see anymore. But if you do, I actually wrote something a long time ago called derivation, and this actually shows you how you can derive all these equations. Never have to do that when you solve them, though. This is just showing the theoretical underpinnings using your Math 32 knowledge and all this stuff, which I just stopped lecturing on because it's just a waste of time because it doesn't help you solve the problem. It's the theory behind it, the mathematical foundations of the solutions that you get from these things and why they actually work. Okay, but really, what you got to do on the test is you got to do the how. You got to know how to do it. It's not so much the why. If you're really the kind of person that worries about the why, that's what the notes are for. Okay, and what happens is the solution is going to be, when you have this kind of setup, if you have some initial voltage on the capacitor, like you charge up the capacitor with some voltage, and then you let the energy, you let the capacitor current flow through the resistor and dissipate, what happens is the initial voltage, V, just decays with an exponential solution. So it's just V0 e to the minus t over tau. And the nature of the time constant means this tau is called the time constant, okay? And maybe I can just put another line here. So tau equals the time constant. And for a capacitive circuit, an RC circuit, it equals 1 over RC. That should, you did that in, maybe you did that in physics 3, right? Yeah. Okay. 1 over RC is the time constant. And if you've got a one-time constant into that exponential, you've dropped to about 36.8% of the original voltage. And the time constant basically determines how fast the signal decays, how fast the voltage will decay, will discharge from that thing. And what it means is, if the time constant gets really small, it decays really fast. If the time constant is really big, it decays really slowly. So that's the, I'm sorry, tau equals RC. What's confusing is that you actually put the it's T over RC. Yeah, it wasn't making sense to me, right? So as R gets bigger and C gets bigger, the time constant gets bigger, and that means it has more capacity of charge, and so it actually takes longer to discharge that thing. And as the resistor gets smaller, the capacitor gets smaller, there's less charge on that capacitor, so it gets released a lot faster, and the voltage drops faster. The key to working with these circuits is just finding the initial voltage on the capacitor and whatever that was, and the time constant T, tau. And once you know what R and C is, you know the initial voltage, you can actually construct the solution real quickly. The only trick is sometimes the circuit has some complexity to it, like in this case. So here's your example 1. And so you got your handout, pull up your example 1. And we're going to insert a text box. And now we're going to solve it. So now they actually said assume that. So they're giving us a circuit here, and they're defining I/O and Vx. And they're saying assume that Vc of 0 equals 30 volts. And they're giving it to us, right? Sometimes we have to derive Vc of 0, but in this case, they're giving us capital V0, the initial voltage on that capacitor, right? So that equals V0. I'm just going to add that here to the right. It equals V0. And what's tau? Yeah, but what's the resistor in this circuit? That's the trick. What is the resistor? So tau, of course, is R times C, and C is pretty obviously 1/3 of a farad, but what's R? Yeah, so R is the equivalent resistance seen by the capacitor. Yep. No. Yeah, 12 in parallel, 6 in series of 8. So R equals 12 in parallel with 6 plus 8, which is going to give us 12 in parallel with 6 is, I think, 4. So that should give us a total of 12 ohms. And so therefore, tau is just 12, which is the resistance in ohms, times 1/3 of a farad, and that's going to be in units of seconds, so that's going to say it's a 4-second time constant. And that means, therefore, we know what the solution for Vc of t is now, right? It's just, so Vc of t is going to be V0, I'll just write out the formula, e to the minus t over tau, and I can actually exponentiate that thing not too bad, I think. Where is that? You know, it's annoying. Even in, you have to click on these menus just to make a superscript. It's like ridiculous. Okay, so it equals e to the minus, V0 e to the minus t over tau, and that equals 30, because that's V0 given to us, and then it's just e to the minus t over 4. Okay, and that's the answer, or it's e to the minus 0.25 t. Let me shrink these down a little bit. And now, what about, it's also asking us to find Vx. What about Vx of t? Looking at that circuit, what can you say about Vx? If you know what, there's a really simple way to find Vx. If you know what Vc is, what's Vx? Sorry? Well, that's one way to do it, but there's a real easy way to do it. I'm talking voltage divider. Yes, it's a voltage divider. So it's a voltage divider of Vc. And that means it's just the voltage, it's the resistor combination of 12 parallel with 6, right? That's the voltage, that's the resistor that Vx is being measured across, right? It's being measured across this 12 ohm and that 6 ohm resistor in parallel, divided by the sum of the total resistance, which is, we've already determined, is 12 ohms, right? So it's just going to be Vc of t times 12 parallel with 6 divided by the total R, like that, which means it's going to be 4 over 12 times Vc of t, which is going to be 1/3 of Vc, which is going to just be 10 times e to the minus t over 4. Okay, and but what about I/O? How are we going to find I/O? So basically, everything is found from DC. But now, how do we know? If we know what DC is, how do we find IO. IO equals what? If we know VC, what's IO?
For the last one, you need to include the 30 with your natural number.
Well, VC has 30 in it.
But it's VC equal 30 times V to the negative T over 4?
Yeah, so VC is 30 e to the minus T over 4, and then because of the voltage divider, we're multiplying VC times 4/12. Yeah, good. I'm glad you asked that because you don't want to be confused about that. Yeah, so instead of writing 30, I mean, I could have written 30 e to the minus T over 4 here instead of VC. And then that would also show what's happening there. Yeah. So IO, if I know VC, what's IO? So yeah, you could do KCL at this node. What could you do? What else could you do? I'm going to find what's the easiest way to find IO. Current divider, I don't think that. I mean, if you wanted to find the current through one of those branches, you'd find IO and then use the current divider through, like, one of those parallel paths. But Ben, what do you think? How would you find IO? I know VC. What's IO? Yeah, there's a kind of a formula. So suppose VC was 12 volts. What would IO be? Suppose I knew VC was 12 volts. What would IO be? Yeah, right. It would be 12 volts divided by what?
The total resistance
between the two ends of that capacitor, right? Yeah, don't jump to that 8 ohm because that's not taking you all the way there, right? You got to go through the 8 ohms, then you got to go through the 12 parallel with 6 ohms, right? So it would be, if VC was 12 volts, it'd be 12 divided by the total resistance from one end of that thing to the other, right? So that would be 12 divided by 12 ohms, so it would be 1 amp. But it would be negative because it's going in the opposite direction of the current that would be driving from VC, right? Because that capacitor is now driving, it's sourcing current into that circuit like a battery. So it's a battery that has a very short lifetime. Right? It just runs down really fast. Right? That's what's happening to that capacitor. So IO is going to be minus VC divided by R equivalent. I'm going to just call this R equivalent. It's the R equivalent seen by the capacitor, that total resistance. So it's going to be minus, 30, minus 30 e to the minus T over 4, and then divided by 12. See, this is what you do all the time when you're using PowerPoint. It totally screws up the font every time. Okay, so what do we get then if we have, it's going to be, sorry, minus 2.5? Sounds right to me. So it equals minus 2.5 e to the minus T over 4. Okay? So that's our first example. Okay, now quite often the circuits are a little bit more complicated. So in this example, they gave us the initial voltage. They just handed it right to us. In general, we're not given that initial voltage. We have to derive that initial voltage. And what we're given is often a circuit now with a switch in it. And when you're going to do this in the lab, you're going to do this not this week, but the week after. Actually, you're going to work with switches this week when you're going to get to do work with transistors and diodes tomorrow, just to kind of get an experience how those things actually work. You can make a little flip-flop. But switches are, the switches we're going to be using are these momentary contact switches. You can make them connect two wires or break a connection between two wires when you let go of the switch. And here's the symbol for a switch in the circuit. This is the first switch we've kind of seen so far. And the switch is, it tells us here it's open. Oh yeah, it's closed and then it's open at T equals 0. So it's initially closed. It's initially closed and opened at T equals 0. Okay, so that circuit's been closed for a long time. Okay, and the question is, we got to find, in order to find the solution, we have to solve this, right? We have to, so the plan is going to be A, we got to find what is V0 before the switch opened. B is then we got to find tau again, and to find tau, that means we got to find R equivalent seen by the capacitor. And when we get all those three things together, and then tau equals R equivalent times C. when we get all those pieces together, then we can just sort of assemble the formula for the solution for V. V of t, again, is the voltage across that capacitor for t greater than or equal to 0. Okay, that's the plan. Okay, so who wants to help me execute the plan? So in order to find VO, okay, so for A, VO equals what? Remember now, you got to imagine that circuit is that switch is closed, okay, and the circuit's been in a steady state for a long time.
Can you do a voltage divider?
Yeah, and what does that capacitor turn into when that switch has been closed for a really long time? An open circuit. And so really, what V is just measuring the voltage across those parallel 12 parallel with 4 ohm resistors, right? And it's a voltage divider formula relationship, right? Because you got that 6 ohms here in series with the combination of 12 and parallel with 4. And so V is going to be the voltage divider. VO is going to be the voltage divider of 12 parallel 4. Right, it's 12 parallel 4 divided by 12 parallel 4, plus 6 times 24 volts. I'll shrink that a little bit. So, right, it's the ratio of this parallel combination resistance divided by the total resistance across that voltage source, that 24 volt source, times the voltage source itself, right? And so that equals what's 12 parallel with 4? Okay, that seems 48 over 16, right? Yeah, so it's 3 divided by 9 times 24. So that equals 8 volts, right? Okay, that's our initial voltage. So all these things we learned, in previous classes keep coming back to us in different forms. We've got voltage dividers, we've got current dividers, we've got all these things happening. What is the R equivalent seen by the capacitor?
Is that before or after the circuit and the switch open?
Well, that's kind of a good question to ask. What do you think it should be?
After.
Yeah, it makes sense to be, if we're looking for the response after the switch is open, it's going to be depending on the resistance that the capacitor sees after the switch is open. And it's not the same as what the capacitor sees before the switch is open, right? Because before the switch is open, you got another parallel path of that 6 ohm resistance there. But after the switch is open, all that capacitor sees is 12 and parallel with 4, right? Okay? So this is, you might say after the switch opens, right? That's just 4 in parallel with 12, which is 3 ohms. And so so we know that's the R, and so we know that the capacitor equals, we're given it's 1/6 of a farad, so that means tau is going to be R times C, which is 3 ohms times 1/6, which is 1/2 of a second. And so therefore, V of t, and now we just assemble all those pieces, right? It's just V0, so it's 8 times e to the minus 2t, because when you take t over tau, and tau is half a second, it becomes 2. So 8e to the minus 2t. Okay? It's really not that bad, right? It's fun. It's a nice break from Thevenin equivalence, which you're going to have to tackle one last time, one onslaught before the spring break. Okay. Well, what about inductive circuits? Well, you can do the same thing with inductors, and with inductors, you can solve. Again, you can solve. Well, for inductors, we tend because V of the inductor is the derivative of the current. So we can use KVL to solve for inductors. And KVL around that circuit says that if we do KVL going clockwise, we're going to see starting at the lower left corner, we're going to see plus VL, right? So we see plus VL plus VR equals 0, right? And what's VL? According to your nifty formula sheet, VL is what? Yeah, so L di dt is VL plus I times R equals 0. Okay, so this is the law for the inductor. This is Ohm's law again for a resistor. And again, solving these things, you basically say, okay, di over I equals minus R over L dt. You solve it. This is your differential equation technique. You should kind of have, this should look familiar. If not, I apologize, but you might need a refresh, a brain refresh. And so the solution is going to be I of t is going to equal some I0, the initial current, going through the inductor times e to the minus t over tau again. And again, tau is defined a little bit differently than with the capacitor. Can you see it on your formula sheet? Yeah, in this case, tau is going to be L over R. I always get mixed up on those. I even mess it up for the capacitor. It's tau is RC for the capacitor. It's L over R for the inductor. Keep that sheet handy, because if you mess that up, you're going to get a totally wrong answer, right? So, yeah, so tau is L over R. So here's the solution of the inductive source-free RL circuit. And again, you know, I equals I0 e to the minus t over tau. And tau equals L over R. Okay, important to be aware of. I'm not gonna superscript that stupid thing. One other nice, interesting thing is this about this exponential, which you'll actually get to work on in the lab. You can measure the time constant of a RC or RL circuit in the lab with an oscilloscope, and you're going to get to do that in a couple of weeks a week after spring break. And it turns out that the slope, the initial slope, starting at 0, right at that I0 point where it's right there, and the initial slope, once it starts to decay, if you take a tangent to that initial slope, it intersects the horizontal x-axis, the t-axis, at tau. So if you actually set up a square wave going into one of these RL or RC circuits, you're going to get this decaying exponential on an oscilloscope. And you can estimate what the time constant is by looking at the scope and trying to figure out how far it is before the tangent to the decay curve intersects the horizontal axis. And you'll get to do that in the lab, but not this week. So here they are in comparison. You know, you've got the RC source-free circuit, and it's source-free because we're switching off the source and letting the whole decay process happen by itself. It's either I0 e to the minus t over tau for an inductor RL circuit, or V0 e to the minus t over tau for a capacitor circuit. So for us, we're going to have to find the initial current I0 before the source was taken away, and the initial time, or the time constant during the region of interest, L over R. And R, again, is the equivalent resistance seen by that inductor. Okay, so example 3, we have 3 minutes. I think we can solve it. It's actually not too bad. They're giving us I0 is 5 amps, right? That's capital I0. That makes that part pretty easy, right? So all we got to do is find out, we've got to find tau, right, which is going to be R equivalent seen by the inductor times the L of the inductor. And what is the R equivalent seen by the inductor is going to be 10 in parallel with 15, right? Which is going to be 6 ohms. Okay. So therefore, I of t equals, now they're telling us I0 was 5 amps, so it's going to be, again, I0 e to the minus t over tau. And superscript that baby. And tau equals L over R, the equivalent, which equals 1/6 divided by 6. So that equals 1/36 of a second. I don't know what that thing is. You can go away there. Oh, that might have been another answer. Okay? So that's tau. So that means I of t is going to be 5, and it's e to the what? It's t over tau, so you got to reciprocate that, so it's 36t, right? E to the minus 36t. Okay? Now, what about Vx? We'll kind of end it with this one here. What about Vx? This is where there's another nice nifty formula to help you find these real easily. What are we going to use? Current divider. Yes. So basically, and this is the thing, an inductor, kind of like a current source. It's a time-varying current source, right? It's actually got some initial value, it's decaying, but it's pumping current. Capacitor, kind of like a voltage source, right? Temporarily, it's going to decay pretty fast, but for a short period, it's pumping current as well. You know, it's forcing a certain voltage that's decaying, forcing current around that circuit. So these are like little sources that are going to just die out really fast. And while it's a source, we can apply the current divider formula because if we want to find Vx, we've got to apply Ohm's law on the current that goes through this particular branch of the circuit, right? So Vx is going to be Ix. Now Ix is going to be going down, so Ix times 7, right, is going to be Vx. If we define Ix as going down, okay, can you imagine Ix? You might draw Ix pointing down, right, on your sheet. I can't do it. It's too hard for me to do it. Ix is pointing down from the plus to the minus. It's going downwards through the x. So, and it's Ix times 7. But what's Ix? Well, Ix is going to be the current divider of I, but there's a sign problem, right? So what's that going to be? It's going to be I of t times what? What does the current divider formula say?
Oh, it's 3 divided by 10.
It's the other resistance. It's 15 divided by 25. Okay? Right? It's 15 divided by 10 plus 15. It's the other resistance divided by the total resistance of both optional paths. Okay, times IT. And it's negative, right? Because it's actually in the opposite sense. The current's going to be flowing upwards through that resistor because that current source is pushing it down through the inductor. So it's going to come out and squirt up through those resistors upward. Okay, so that's 15 over 25. What is that? That's is that 3/5? 3/5 of 5. So that means it's going to be, and then all of that's going to be times 7. Don't forget the 7. So it's going to be 3. I think it's going to be minus 21. Is that right? Minus 21 e to the minus 36t. Somebody check my math there. 5 times 3/5 is going to be 3, and then times 7 is going to be minus 21. I think, right? Oh, that's the current I. We don't have the answer for the voltage. So the voltage should be something like, it should be minus 27 e to the minus 36t. Okay, and that is it. We made it through almost half of the presentation in spite of all the difficulties. Now I got to figure out what the hell Microsoft did to my computer. Yeah, maybe I can roll it back.
On this right here, you know, and this it kind of gave something like that.
Oh, you're talking about engineering 17?
Yeah. And
You did is this the energy function?
yeah.
Yeah.
So kind of like
You should define C in here.
oh, in there. Okay.
Yeah, the function has everything it needs. It's like a little isolated box. And so you define C in there, don't define C there, you don't need it because it's going to be all embedded in there. Yep.
Okay.
That should do it for you. Yep.
So once again, I'm going to ask you about this problem, which is coming up.
Okay. Let me just start prepping things up there. There should be another class coming in. I'm probably waiting outside for this.